Hi, so welcome back. As you can see, I'm wearing a hat because it's getting late recording videos. So I don't want to disturb my family. I'm outside in the shed and it's pretty cold out here. So anyway, let's just warm up for some dynamic models. I think we can be ready now for that. Okay. So so what is it that we're interested in here in dynamic models? We're interested in finding out what is the effect of the lag dependent variable on the current value of the lag dependent variable as a specific interest. Okay. So the new thing here is that we now have rho times the lag dependent variable. So that is yit in the previous period on the right hand side. Okay. We're still interested in modeling the outcome, the probability that y is equal to 1, conditional on a bunch of explanatory variables. And what we're gonna assume here is that once we have conditioned on the entire past of that dependent variable, um, once we have conditioned on the one period back lag dependent variable, then the entire history of the lag dependent variable doesn't matter. Okay, it's only that particular lag. Okay, so you see here on the right hand side, there's no yt minus 2, right? There's no yt minus 2 over here. So all these conditioning variables, they are captured by this variable alone. Okay, now you may don't like this assumption, and then you would need to include another lag. Okay, but this is really the leading case that we're looking at. Okay, and then also we're going to assume here that set it here is a strictly exogenous regressor, in the sense that if you in the conditioning set here for the probability of yit at time equal to 1, um, have the entire past, present, and future here in set I, there's no subscript t, then it's sufficient to condition only on the current value. So this is an strictly exogenous regressor, okay? But this one is not strictly exogenous. So we have some sort of sequential exogeneity conditional on the unobserved effect, and the particular interest here is in estimating this effect. And we really want the causal effect of the lag dependent variable, what we refer to as, true state dependence if this is different from 0. Okay. Say if you were just doing a probit where you just put in the lag dependent variable without controlling for that unobserved effect, well, then it's really hard to know, is it because of the persistence in the unobserved effect? Or is it we observe persistence in choices? Or is it because of the lag dependent variable, because of the state dependence? And discriminating between these two effects is important because they have very different implications. Think for the dynamics. And so if you think about, for example, a policy that pushed people into the labor market, now we're modeling labor force participation. Okay. So if we push people into the labor market, okay, so now they're in the labor market, y is equal to 1. Then in the next period, they're more likely to be in the labor market again if rho is positive. Okay, so that's kind of, if rho here is positive, then just the fact that we're in the labor market last period makes it more likely that you're going to be in the labor market next period. That's state dependence. Okay, whether you're in the state y equal to 1 depends on whether you were in the state y equal to 1 in the last period. Okay. But that persistence could come from unobserved heterogeneity as well, right? Just maybe there's just some people that have very large CIs, just like to work, all the time, even in the middle of the night with a hat on. Okay, so I have a very high CI. So even if I lost my job, I'm gonna rush out and find a new job another place. Okay, so I really like to work. So I like to think I have high CI. Okay. So, but there's also people with very low CI, and if you try to push those people into the labor market, well, maybe they're not going to be there in the next period, right? Because it's not because of rho that there was persistent in those choices they made, 0, 0, 0, 0 all the time. it was because of that low CI. So these things are important to discriminate between, okay? And actually, even in the case where rho was equal to 0, you'll see, and I'm going to show you some simulations, that if you neglect that heterogeneity and do not appropriately control for it, try to estimate a propit model, then you're going to get a positive coefficient on the lag-dependent variable. And, you know, another way to see it is if you don't control for CI here, right, when you have the lag-dependent variable, well, even in the case where the coefficient on this guy here is 0 up there, you're not going to get that it's sufficient to condition on the sets. Okay, so that's, you know, that's really due to the presence of that unobserved persistent effect. Okay, so it's extremely important to control for that unobserved effect. Sorry about that star. I think it's an attempt to make this bold instead of just emphasized. Okay. Anyway, so then the next question is, how do we deal with it? Okay, we actually already know how to deal with it in static models, right? We had lots of different opportunities. You know, we could try to do, you know, fixed effects with the Logit fixed effects. We could do, you know, the random effects approach. We could, you know, try to proxy for C, or we could do. I forgot all the list, but you know, we could do a random effects approach. Okay? Doing C, estimating that as a coefficient, well, that's not necessarily a good idea. Okay. I talked about the incidental parameters problem that was, you know, resulting in basically inconsistent estimates, not only of those CI parameters, but also of the parameter beta that you're interested in seeing. Okay, well, before we move on, let's just look at you know, that joint density. Okay, the joint density for the sequence of choices, you can always write that up conditional on that unobserved effect, right? And even though we don't observe it, it's a good idea to start just writing that up conditional on things we could potentially conditional. Okay, so here's a sequence of choices, you know, from choice in period 1 up to capital T. We want to model the joint density of this sequence of choices in our dynamic model. And these things are not independent. So you cannot just multiply all the marginal densities together, because they are basically, there's dependence over time because of the lag dependent variable. Okay. But what you can always do is you can always write a joint density as a product of conditional densities. Okay. And then that's what we are doing here. Okay. So let's just start at time equal to 1. Okay, that's the easiest one. Then you have y1 here and only y0 here in this part of the condition set. And of course also set and c. Okay. Then you move on to the next period, period 2. Well, then that's going to be y1 and y0. Okay, and now you kind of see where you're going. This is, you know, basically the history up until today you're conditioning on. And then you just multiply all those probabilities together. This is just a manipulation of conditional densities and joint densities. This is what you get. And this is, I mean, it's a little bit more advanced than what you saw in your, you know, introduction statistics course, but it's the same rules of working with conditional densities and joint densities. Okay, so that's what we're doing now. Now, remember also that we assumed that once we have conditioned on the lag-dependent variable, then the rest of the history it didn't matter anymore, right? So everything about the past is captured by only one lag. Okay, that's what we assumed here. This is what we assume in our model. Okay, I mean, we could assume other types of dynamics, but this is what we have assumed. Okay. And so we can just you know, paste in our model for that particular density, and then we both have the probability that y is equal to 1. Well, this is what we have here, and then we have one minus that probability in case y is equal to 0. Okay, and we just, you know, multiply all these together across the different time periods. Now, so this is that joint density. So what are we going to use that for, right? We, like I alluded to at the beginning, we can't really, use this for the likelihood, because if we want to do conditional maximum likelihood, we want to condition on things we observe. Okay, we don't observe C, so we need to do something about that. And maybe we could do something like we did with the random effects approach earlier, where we were like integrating it out, or we could try to see if we can estimate it or do something else. Okay, estimating it, like I said, not a good idea. The incidence of parameters problem is even worse in this case. Okay, so we want to try to see if we can do a dynamic random effects model. Okay, and integrate that out that unobserved effect, specify a conditional distribution for that unobserved effect, where we also condition on the other things we condition on. That's what we need to do. Like, remember when we were doing the dynamic random effects model in the static context, we would derive the density conditional on the explanatory variables. Okay, the other variables we condition on. Okay, now we not only have the strictly exogenous variables, we also have the initial condition. Okay, so we need to arrive the density conditional on those variables. Okay, I mean, we can't observe this guy. I mean, this is just the observation of y in the first period, so we can condition on it. Okay. See, now comes the problem, right? If you're writing up a conditional density of Ci conditional on y and z, you don't want to assume that it's uncorrelated with y0. Okay, why? I mean, stop to think about that. Why? If y had 0, has no effect on C, or is not correlated with C, how can it be C be correlated with with y1, right? I mean, it's appearing here, right? So it's you got your C here. It has an effect on yt for period 1, 2, 3, 4 up to capital T, but not on y0. That's very unrealistic. So that's not really a good assumption, and we don't want to make that assumption. Okay, so we want to actually allow for some dependence between Ci and those initial conditions. Okay, otherwise we're going to get something funny. Okay, and you can see, I mean, if rho is positive, then that there must be some kind of dependence between the initial condition and C. Okay, so this is what we refer to as the initial conditions problem. So you have now not only one problem of dealing with the unobserved effect, you also have this other problem, this additional problem, that the unobserved effect is potentially correlated with initial conditions, which we call the initial conditions problem. Okay. So there's several approaches to deal with it. One thing is to assume it's not there. Like I said, if we treat this as completely fixed and assume independence between the unobserved effect and Ci, well, we would not have a problem, but that's like assuming the problem is not there. This is a very strong assumption. It's not a good idea. We need to do something about it. Okay. Then there is the what we call the Woolridge Chamberlain approach. Okay, so Chamberlain, he was a guy who suggested we'll do not only a random effect model where the random effect had mean 0, but a random effects model where we allow for some correlation with the explanatory variables in a specified way, in a way we specified. Say, for instance, we included the averages of the individual specific averages of the explanatory variables over time, to kind of allow for some dependence between Ci and between Ci and those variables. Okay, so that we had some correlation. Maybe we're worried about that. Okay, but then the idea here is now that we're also conditioning on y. Maybe we should also include that in that conditioning set in our correlated random effects model. So really, assuming, for example, that you have C conditional on y naught and Z conditioning on the initial condition and the strictly exogenous variables is normally distributed with some specified functional form for the mean. Okay, you can also even try to allow it to depend on the variance depend on it as well, and you will have some kind of way of modeling heteroscedasticity in that model. We're not going to do that. We're gonna work with this. Okay. There's some other approaches where, by Heckman in his 1981 paper, where he's doing an approximation of the initial condition with some pre-sample information, write up a separate model for this, and then you multiply that probability as the last probability here in that sequence. Okay, so you have like a separate model just for that particular that first observation. Okay. Anyway, we're not going to do that. We're going to do the Woolridge Chamberlain approach. I'm going to show you exactly how to do it. Okay. Then there is the some semi-parametric approaches, we'll call it. We are working within parametric models all the time here. So we are essentially assuming, a full structure for that probability that y is equal to 1. Okay. We have a full parametric model. That distribution is essentially the distribution of the dependent variable is known up to a set of parameters, okay? Because you assume the functional form for G, and you assume the functional form for this conditional distribution for C. You, for example, assume that it's a normal distribution, which is a parametric distribution. Once we know that functional form, well, then we know everything up to the parameters that we are putting into that model. Okay, so it's a fully parametric model. What they're doing here is something else. It's like a fixed effects approach where they are not making any distributional assumptions on C. They are really trying to get rid of C with some tricks that are similar to those tricks that we're making in the fixed effects logit. So what they are doing is a fixed effects logit, and the logit probabilities, they are, parametric functions, right? And then they're agnostic about that distribution here, okay? So there's a nice paper in Ecometrics at 2000 by Bo Honoré, who's a Danish professor at Princeton, and then Kyriasidou, I hope I pronounced that right, where they do this. One of the things in their paper, by the way, that you are able to estimate that, test for that state dependence in a very robust way, but you're not, just like in the fixed effects approach, fixed effects logit, you're not able to identify anything else but the effects on the log odds ratio. Okay, so you can't identify the average partial effects and the partial effects because you don't know the distribution of C is. And that's kind of a general principle in econometrics. The less you assume, the less you can identify. Okay, I mean, the less you, in a proper way of saying this, it would be nothing in, nothing out. Okay, if you put little in, you put a little out. Okay. Okay, so back to Woolridge Chamberlain. Okay, this is a simple solution to this initial condition problem. Actually, the title of Woolridge's paper, I think it's called something like actually a simple solution to the initial condition problem. So what we'll specifically assume is that C conditional on the initial condition and the strictly exogenous variable set is normally distributed. Okay. Now the very nice thing about the normal distribution is that you can write it you can write one normal distributed variable as a sum of others, and they'll be normally distributed. Okay. Here's one other normally distributed variable, AI, that is our random effect. So we'll just call that AI now. Okay. And then we add a bunch of stuff here that's going to add to the mean. None of those are stochastic variables. Okay. So this is just the mean here. That is just another way of writing C. Okay. Okay. And this has variance sigma A. Okay. And it's normally distributed. Okay, so the cool thing in the probit model is that if this is normally distributed and this is normally distributed, well, you can just add them together and they're both normally distributed with the mean equal to the sum of the means of those two. Okay, so that's very nice. And this is essentially what we do. So we can just substitute that equation in for CI. Okay, so so here again, we essentially have the specification for another probit model. Okay, it's a probit model that has this combined error term, but we can estimate this with a random effects probit, standard random effects probit, just like we did last time, but now with an additional set of regressors. So this is why it's kind of simple. You know how to do the random effects model. So now you know how to do the random effects model with lag-dependent variable. You just put in the lag-dependent variable and then your controls for the initial conditions and whatever dependence you want to allow between the strictly exogenous regressors and that unobserved effect. Okay. So that's relatively simple. If you think about, you have standard software like Stata or the code that we're writing here, you can just put in a bunch of more exponential variables, and then you've controlled for those initial conditions. Very, 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 very elegant. Okay. So I guess this is essentially what I'm saying here. You can estimate this by a standard random effects probit, this estimating equation here. And then you just simply add the y naught and set I in the conditional and set to take account for the initial condition, and then any specified correlation between CI and set I.